Today in the workshop, we'll be working with servo motors. We'll learn how these versatile little devices work and how easy it is to control one using an Arduino. We'll then look at the PCA 9685 module, which allows you to control 16 or more servo motors using the I2C bus. We're moving into the right position, so welcome to the workshop. Hello and welcome to the workshop. Today we're going to be making things move with servo motors. Now we've used other types of motors in our projects before and we've looked at them in depth. We took a very in-depth look at stepper motors not too long ago, and we've used DC motors as the basis for a number of robot car designs that we've done. We also looked at the L298N, which is an H-bridge module capable of controlling DC motors. But although we've used servo motors in some of our projects, we've never really taken an in-depth look at them, and that's exactly what we're going to do today. Now, I should mention that when I'm talking about servo motors, I'm not talking about industrial type servo motors, which can be very huge things that can cost hundreds or even thousands of dollars and that have digital control type of systems. I'm also not talking about the small hobbyist digitally controlled motors, which are used in specialized applications such as model airplanes and model helicopters. I'm speaking of your standard garden variety analog servo motor, the type that has 3 leads that we've seen in a number of our Arduino projects. These things are great for robotics. These things are great for IoT projects. They're inexpensive. They have a lot of torque. If you need to move a sensor or a camera somewhere, they're absolutely perfect for that. Anytime you need to position something precisely and that you don't need to go a full 360 degrees, an analog servo motor might be exactly what you're looking for. So let's start taking a look at servo motors now. So let's take a look at servo motors. A servo motor is a motor whose shaft position can be precisely controlled. It uses an internal servo mechanism and some gearing in order to accomplish this. The servo mechanism provides positional feedback so the motor always knows what position its shaft is currently in. Servos are used in industrial and in hobbyist applications. We'll confine our discussion to hobbyist servo motors today. Hobbyist servo motors use DC motors internally. A potentiometer is used to monitor the shaft position and act as a feedback sensor. An internal controller board connected to this potentiometer adjusts the position of the servo motor until the shaft is in exactly the required position. The shaft position is controlled using pulse width modulation. In a common hobbyist servo motor, a pulse width of 1.5 milliseconds will cause the servo to rest at the 90-degree position. Reducing the pulse width to 1 millisecond will cause the servo to go to the 0-degree position. Increasing it to 2 milliseconds will cause the servo to move to the 180-degree position. Most hobby servo motors travel a range of 180 degrees. 270-degree servo motors are also common. You can also get continuous rotation servo motors. These are servo motors that have had the potentiometer internally removed. In a continuous rotation servo motor, a pulse width of 1.5 milliseconds will cause the servo motor to come to a stop. A pulse width of 1 millisecond will cause it to spin counterclockwise at full speed. A 2 millisecond pulse width will cause the servo to spin clockwise at full speed. Hobbyist servo motors have a 3-pin connector. However, the color codes used by different manufacturers tend to differ. Pin 1 of the servo is the ground connection. Pin 2 is the power connection. And pin 3 is the control line, the line that the pulse width modulation signal is sent to the servo motor on. So now that we've seen how servos work, I've got a few of them laid out here on the workbench for you. Now, this is basically your standard servo motor. This is an SG90. It's got plastic gears. It's a very, very common servo motor. You can usually get these in bags of 5 or 10 for a very low price on eBay or Amazon. This is a much larger servo motor, as you can see. An HS422, has a lot more torque, etc. Operates the same way that this SG90 does, except it's capable, of course, of a lot more power, and it consumes more current. And this looks a lot like the SG90, but this is an FS90R, and this is a continuous rotation servo motor. So as you can see, it's the same size and form factor as a standard SG90, so you can fit it anywhere that you could mount an SG90. But this is continuous rotation, and on the back, I don't know if you can see this, there's a little adjustment. You won't find any kind of adjustment on the bottom of this one here, but you'll find an adjustment on the continuous rotation one. This is in order to zero the motor. What you do is you give it the 1.5 millisecond pulse that we use to set the motor at its 0 point, and then you adjust that until the motor stops, and that way the motor is set up correctly. Now, these are a number of the attachments that you get when you get a servo motor. I've got a few of them out here. These are sometimes called arms or horns, and these attach to the front of the servo. As you can see, all of my servos have attachments on the front of them, and this is how we mount things to our servo motors. And so you'll find a lot of projects that are made for servo motors are already made to accept these mounts and horns that come with the servo motors. So that's just a look at a few of the different servo motors that we will be working with today. Two of the key specifications when selecting a servo motor are speed and torque. The speed of a servo motor is specified as the time required to move the shaft by 60 degrees. For example, 0.25 seconds per 60 degrees indicates that the shaft will move 60 degrees in a quarter of a second. Torque is defined as the amount of force a servo motor can apply to a lever. It is measured in ounce inches or kilogram centimeters, and the two measurements can be converted. I have a resource on the article on the website that will allow you to do that. An example, a servo motor rated at 5 kilogram centimeters means that 1 centimeter from the shaft position, it can support a weight of 5 kilograms. 2 centimeters from the shaft position, it'll support half the weight, 2.5 kilograms. Half a centimeter from the shaft position will allow it to support double the weight, or 10 kilograms. There are a number of torque specifications associated with a servo motor. The rated torque is the maximum torque at the servo's rated speed. The stall torque is the amount of torque that will cause the motor to stall. Peak torque is the maximum torque for very short time periods, usually measured in milliseconds. By knowing the speed and torque requirements of your application, you can select the proper servo motor for the job. So now we've seen how a servo works, and we've seen some of the specifications that you would use when you're choosing a servo motor. Now another specification, of course, that you're going to want to specify is the size of the servo motor. And as I showed you before, I've got a couple of different size servo motors here on the workbench. I've also got something else on the workbench here that I wanted to show you. This is a little testing device. This allows you to test a servo motor. It's a very handy thing to have in the field. People who work with model airplanes and helicopters and that often carry one of these around just to make sure their servos are working. And I want to show you how that works. Now this device is disconnected to my 5-volt power supply. You can use any 5 or 6 volt supply to power it. And you simply plug a servo motor into it. So I'm going to plug this in. Make sure you plug it in the right way around, of course. And it's got 3 different modes. On one of them, the mode I'm in right now, as I turn the dial on the device, the servo motor turns, and that basically just shows that the servo is working. The second mode, and you press a little button over here, there's a little push button switch under here. This just zeroes the servo motor, so this should be at the 90-degree mark right now. And in the third mode, it sweeps it back and forth a little bit so you can watch the servo work. I'll show you that with another servo over here. This is just a standard servo motor. Plug it in and we'll zero it, sweep it back and forth, or just manually adjust the position. Now, of course, I also have a continuous rotation servo motor. Let's see what happens when we plug this into the tester. You'll notice it's continually rotating. And I can adjust the speed to a point in the middle where it'll stop, and then adjust the other way, it'll go in the other direction. And of course, the second mode here should cause it to stop. If it hadn't stopped, I could adjust my little set screw here until it did. And the third mode will just spin it back and forth in the 2 different directions. So there you have it. It's a handy little device. They're only about $2 or $3. So if you're going to work with servo motors, I would advise you pick one of these up. So now that we've seen how servos work and how to specify them, let's go on and actually do something practical with our servo motor. Okay, so now it's time to do our first Arduino servo motor experiment. Now before we hook this up, there's one thing I want to mention. You may see a number of other diagrams, including on the Arduino website itself, where they've hooked the servo motor up to the 5-volt power supply from the Arduino Uno or Arduino Mega. You can do that if you really need to, but I would advise against it. I always power servo motors and any type of motor with its own independent power supply. Motors tend to put noise on the power supply lines, and that can affect your digital circuitry. They also can have sudden current demands, and that can also cause a spike, which can reset your Arduino or cause it to act erratically. So I would highly recommend that you use a separate power supply, a 5 to 6 volt power supply, for your servo motor experiments. I'm using the power supply on my workbench, which is a 5-volt supply, to do all of the experiments that I'm doing. Now, if you absolutely must use the Arduino, you don't have a 5-volt supply, all the power supply stores in your neighborhood are closed right now or something, well then what you could do is put a capacitor, something of 100 microfarads or more, across the power supply line from the Arduino. Make sure to observe the polarity on that capacitor, and that'll act as a bit of a reservoir so that if your servo motor has a sudden load on it, it won't put a sudden spike onto the power supply line, which could affect the Arduino. So now that I've said all that, let's take a look at the hookup for our first Arduino servo motor experiment. For our first experiment, I'll be using an Arduino Uno, although you can use a different model of Arduino if you wish. You will also, of course, need a servo motor. And you will need a power supply for that servo motor. It is not a good idea to run a servo motor directly off of the Arduino's 5-volt power supply. A supply of 5 to 6 volts DC will suffice for most hobbyist servo motors. We'll begin by connecting the ground of the Arduino to the negative side of the servo power supply. We'll then connect the ground of the servo motor to the same connection. Next, we'll connect the positive side of the servo power supply to the servo power connector. And finally, the servo control line will be connected to pin 9 of our Arduino. So the first sketch we're going to look at is a very simple one, and it's included with your Arduino IDE as one of the example sketches. So just go up to File, and then go into Examples, and go down to Servo, and you will see two sketches, Knob and Sweep. We're actually going to look at both of these sketches, but let's look at Sweep first. So this is a Sweep sketch. Now what the Sweep sketch does is it just takes a servo motor and it sweeps the shaft from 0 to 180 degrees and then back again, and it continues on and on and on. So it's a very simple sketch, but it shows you how to use a servo motor with an Arduino. Now, to begin with, we'll include Arduino Servo library. This is a library that's already been included with your IDE, so you just need to have a statement here to include the library. Next, we're going to create an object, and in this case, we're calling it My Servo. And as it notes here, you can create multiple servo objects on one Arduino board. Keep in mind, every servo needs to be associated with a pin that's capable of PWM. The next thing we do is we define an integer called pause. Now this just takes the servo position, and we'll define it as 0. We're going to sweep that from 0 to 180 degrees. Then we go into the setup, and we simply attach the object we've created, My Servo. We attach it to the pin that the servo motor control line is attached to, which in our case is pin number 9. So if you've used a different PWM pin, you can just change the 9 accordingly. And then we go into the loop, and the loop is basically a couple of for loops. The first one going for 0 to 180 in an increment of 1. It steps up from 0 to 180 in an increment of 1, the value of pause, and for every step it writes that value over to the servo motor, delays for 15 milliseconds, and then continues the for loop. So this will go from 0 to 180. Now when you do a My Servo write, whatever value you put over here is the actual angle that the servo will go to. So if I put a 90 there, the servo will go to the 90 degree position. A 45 will send it to 45 degrees. So this will sweep it from 0 to 180. And then we have another for loop which does exactly the opposite. It starts off at 180 and drops down to 0, and will just write pause from a value of 180 down to 0 and delay by 15 milliseconds. And then after that we complete the loop and start it all over and over and over again. So this will sweep our servo shaft from 0 to 180 and then back again. So now let's take a look at that in action. Alright, I've got everything hooked up on my breadboard right now. I'm using the bench power supply on my workbench to supply 5 volts for the servo motor, and right now it's just disconnected. Otherwise the Arduino is actually running and everything is going, so as soon as I connect up the power we should see the sweep sketch in action. And there we go. Now if you reset the sketch, it'll reset the servo. There you can see the servo position reset to the end there. And that's basically it. So now let's take a look at another sketch that we can use to control our servo motor. So now that we've seen the sweep sketch, let's take a look at another sketch that's also part of the Arduino library examples. This one's called the knob sketch. Now you're going to need an extra component for this sketch. You're going to need a potentiometer of 10K or more. So let's take a look at how we wire that up, and then we'll move on to the knob sketch. For our next experiment, we will leave everything hooked up as we had in our first experiment. We will add a potentiometer to the circuit. Any value of 10K or higher will suffice. We'll start by connecting one end of the potentiometer to the 5-volt output from the Arduino. The other end of the pot will be connected to the ground of the Arduino. and we will connect the wiper of the pot to the analog A0 input on our Arduino. So let's take a look at the knob sketch. Now once again, this is one of the demo sketches that was included with your Arduino IDE. So just go into your example section on your sketches and go down to Servo and load up knob. Now we start off by including the Arduino Servo library. So we'll include the Servo library. And once again, we define an object called MyServo that represents the servo motor. Then we'll define a couple of variables. The first one is pot pin, and that's the pin that the potentiometer is connected to. So we've connected it to analog pin A0, so we're defining that as a 0. And then an integer called value, and that's the value that we're actually reading from that pot. And we'll go into setup, and the only thing we do in setup is we attach the MyServo object to the pin that we're using. So again, we're using pin number 9 for our servo motor. And then we go into the loop, and it's very, very simple. We assign val to the value of an analog read on the pot pin. So this will give us a value from 0 to 1023, depending on the position of the potentiometer. Then we'll take val and we'll change its value using a map command, and we'll go, the val is going to be our variable, and it's going to go from 0 to 1023, and we'll map that to a range of 0 to 180. So this will give us a different value for val, and that will represent the angle that we want to turn our servo motor shaft to. And we'll do that with a MyServo write, and we'll just write that value to it, delay by 15 milliseconds, and then go and repeat the loop over and over again. So the result is the servo shaft should go to the position that we've got the pot in. So let's take a look at it in action now. Now I've got the deluxe servo motor demo hooked up for you today in the workshop. I've got not one but 2 servo motors hooked up to my Arduino, and it was quite easy to hook 2 servo motors up. I'm using the bench power supply, so I've got plenty of current for both servos, and the control line on each servo is going to pin 9 on the Arduino. So the only difference between this and the schematic I showed you is that there's essentially a second servo motor in parallel. Now there's a difference between these 2 servo motors. The one here with the single arm is a standard servo. This is an SG90, which is a very common servo motor you've probably used in projects before. It's a little plastic gear servo that's very inexpensive, and it's sitting at the 90-degree position right now. Now this is a continuous rotation servo motor, and it's at the stop position right now. It's in the same body as an SG90, so you can mount it anywhere that an SG90 can go. But again, this is continuous rotation, so it can be made to rotate in one direction or the other by varying the pulse width going to it. Now in order to monitor the pulse width, I've got an oscilloscope hooked up today, and you can see right now that a 1.5 millisecond pulse is being given to the servo. This is the pot I'm using to control everything. And with that size of pulse, this servo motor here, the standard one, is sitting in the 90-degree position, whereas the continuous rotation servo is in the stop position. Now I'm going to move the pot, and you can watch the scope as the moment I'm going to shrink the size of the pulse, and the standard servo is moving clockwise right now, and this is spinning clockwise right now, the continuous rotation one. And the smaller I make the pulse, this is right now at the end of its travel right now. It's gone the full 180 degrees. And this is spinning at full speed clockwise. Now I'm going to widen the pulse again. And as I do, you can see this servo moving back toward the 90-degree mark. And this is slowing down. We come to the middle, and once again, we're at the stop mode. And then I'll go in the other direction. And as you can see, the continuous rotation servo is now spinning counterclockwise. And this is moving more toward the 0-degree position. And look at the oscilloscope. You can see that the pulse width is increasing. And as the pulse width increases toward its maximum, This is down towards 0 degrees, and this is spinning counterclockwise at full speed. And so I've used a knob sketch to demonstrate the operation of both a standard and a continuous rotation servo motor. So from the examples we've looked at, we can see it's pretty easy to control a servo motor using an Arduino. And you can control a couple of servo motors with an Arduino. You need to be using pins that are capable of pulse width modulation. And an Arduino Uno has 6 of those pins. Other models of Arduinos have different numbers of PWM-enabled pins. But if you're going to control a lot of servo motors, you're going to run into a problem. First of all, if you need to control more than 6, you're going to run out of pins if you're using an Arduino Uno. Secondly, the servo library itself makes use of some of the Arduino's internal timers, and that may conflict with some of the other libraries that you're using for other sensors. So that can be a problem when you're controlling servo motors, even if you just have 1 or 2. If you need a lot of servo motors, you can be taking a lot of your processor's resources just controlling servo motors. There is a better way of controlling servo motors with an Arduino or a Raspberry Pi or any microcontroller or microcomputer, and that's to use an external board. I'm going to be showing you a board called a PCA9685. Now the PCA9685 is a 16-channel pulse width modulation control board, so it can control any device that's controlled by PWM, be it servo motors or LEDs, which is another common use for it. Rather than the Arduino, which just controls a servo at 50 Hz, the PCA9685 is capable of a wide range of frequencies to control its PWM devices. Now this is an I2C bus device, so you just connect it to the Arduino or Raspberry Pi using the I2C bus. It just needs a clock line and a data line, as well as a power and a ground. It's got its own power supply, so you can power your servos or LEDs from their own supply, and you don't need the supply from the Arduino. Now it's a really versatile board, especially when you consider that you can cascade more than one of them on the same I2C bus. It's got a number of solder pads on it that allow you to set the I2C address, so you can actually have up to 62 of these boards, and each one of those boards can control 16 PWM devices. Now that's over 900 servo motors you can control with an Arduino. If you have a need to control more than 900 servo motors, please drop me a line and let me know what it is you're building, because I'd love to see something that needs more than 900 servo motors. So at any rate, let's take a look now at the PCA9685 module. The PCA9685 is a 16-channel pulse width modulation controller board capable of controlling both servo motors and LEDs. The board uses the I2C bus and has a configurable address. By configuring different addresses, you can use up to 62 PCA9685 modules on one I2C bus. The module provides a separate power supply input for the servo motors or LEDs that you're controlling. The PCA9685 is on a small circuit board with connections on both ends. The first connection is the ground connection. The next connection is the output enable connection. When this line is brought high, it will disable the outputs. By default, it is pulled low and does not need to be connected. The third connection is the serial clock line of the I2C bus. The next connection is the serial data line from the I2C bus. After that, the VCC connection. This is the logic voltage for the circuit and generally comes from the microcontroller that's connected to it. There is also a connection labeled V+. This is the power supply for the servo outputs. There is another connection for the servo power supply on a 2-pin terminal block on the top of the module. This is the preferred connection as it is reverse polarity protected, whereas the V+ connections are not reverse polarity protected. Next to that connector are a series of solder pads. These are used to configure the I2C address of the module. On the bottom of the module there are 16 connections. These are for servo motors or LEDs. So now that you've seen how versatile this little PWM controller module is, let's use it in an experiment. I've hooked the PCA9685 up to an Arduino, and I've attached 4 servo motors to it. In order to make it a bit of fun, I've taken the 4 servo motors that are in my MeArm. So what I'm going to do in this experiment is use these 4 slide pots to control the MeArm. So let's take a look at how we're going to hook that up, and then how we're going to code for it. For this experiment, we'll be using an Arduino Uno and a PCA9685 PWM controller module. We'll also be using 4 potentiometers. Any value of 10K or higher will suffice. I'll be using 4 servo motors in this experiment. And finally, a power supply capable of powering all 4 servo motors. Anything from 5 to 6 volts should do. We'll begin by connecting the 5 volts from the Arduino to the VCC connection on the PCA9685 module. The ground from the Arduino is connected to the ground connection on the module. The SCL connector on the Arduino is connected to the SCL input on the module. If you do not have an SCL connector on your Arduino, use analog pin A5 instead. The SDA connector on the Arduino is connected to the SDA connection on the module. If you do not have an SDA connection on your Arduino, use analog pin A4. Next, we'll plug in the 4 servo motors. I plugged mine in as follows. Servo 1 was connected to PWM output number 0. Servo 2 was connected to output number 4. Servo 3 to output number 8. And servo 4 to output number 12. If you decide to use different connections, you can modify the code accordingly. Now connect the 5 volts from the Arduino to one side of each potentiometer. Connect the ground from the Arduino to the other side of each pot. Now connect the wiper of potentiometer number 1 to the analog A0 input. Pot number 2 has its wiper connected to the analog A1 input. Number 3 is connected to A2, and potentiometer number 4 has its wiper connected to analog input A3. Finally, connect the power from the servo power supply to the connector on the PCA9685 module. So here's the sketch that I'm using in order to drive the PCA9685 module with my Arduino. Now this sketch makes use of a library from Adafruit, the Adafruit PWM Servo driver library. Now there are a number of other libraries that can also be used with the PCA9685, and I've got links to those libraries in the article that accompanies this video if you want to take a look at some alternate ways of doing this. But at any rate, I need the Adafruit PWM Servo driver library for this sketch, and you'll need to install that into your Arduino IDE, and you can do it just with the library manager. So go up to Sketch, go to Include Library, and then go to Manage Libraries. When your library manager opens, search for Adafruit PWM. And the Adafruit PWM Servo driver library should be the first thing that you see. Now, I've already got mine installed, so you can see it's installed over here. But in your case, if you don't, just click the More Info link, and you will get an install button that will allow you to install the library into your Arduino IDE. Once you've done that, you can load the code, and we'll start taking a look at it. Now the first thing we do is we include the wire library. This is essential for I2C communications on the Arduino. Next we will include the library that we just installed, the Adafruit PWM Servo driver library. Now we define a number of constants. The first two are the minimum pulse width and the maximum pulse width. This refers to the size of the pulses that we are going to be sending the servo motor in order to drive it to one end of its travel or the other end. Now, I didn't come up with these numbers out of the blue. This came with the spec sheets of the PWM Servo driver library, and you can modify these numbers if you find that your servo isn't going from one end of travel to the other, or if you have a 270-degree servo instead of a 180-degree one. The third constant is the frequency that we'll be sending the PWM signal out at. 50 Hertz is the standard for servo motors, so you probably won't need to modify that. Next, we create an object called PWM using the Adafruit PWM Servo driver library. And then we'll define a number of inputs and outputs. There's 4 integers defining the inputs, the 4 potentiometers that we've got connected to the board to control the servo. So that's A0 through A3. And then we'll define the outputs that we're using on the PCA9685 board itself. So these are not Arduino pinouts. These are actually on the PCA9685 board, which has 16 output connectors. And so I've got my motors connected to 0, 4, 8, and 12. If you're using different connectors, just modify the sketch accordingly to represent the connectors that you're using. So now we'll go into the setup. In the setup, we just initialize the PWM object that we created, and so we use a begin, and then we set the frequency of the oscillator that we'll be doing the PWM with on the board, and we set this to 50 Hertz in our case. Now here's a function that actually is really the meat and potatoes of this sketch. This is a function that I called move motor, and it has 2 inputs, the control in, and control in is which of these controls, A0 through A3, are we taking as an input, and also the motor out, and which of these motors are we using. So basically give me the control that we're using, the motor we're using, and we'll set the motor to the value that the control happens to be. Now the way the function works, it first of all defines a number of integers to use internally, and then it takes an analog read of the control that we've passed to it and assigns it to an integer called pot val. Now this will be a number from 0 to 1023, so we're going to change it and create an integer called pulse width, and we'll use a map command to map the 0 to 1023 value to a value between the minimum and the maximum pulse width. So this will represent the size of the pulse width. Now, when we're using the module, the one thing you need to know is the way that it generates a PWM signal. It is a 12-bit PWM encoder, and so what it does is it divides the signal into 12 bits, which is 4096 parts, and it allows you to specify which of those parts you want to start your pulse at and which one you want to finish at. So if you start at 0 and go to 2048, you'll create a perfect square wave. It'll be half on, half off, for example. And so we need to compute what the actual value we're going to give it, the value we're going to tell it between 0 and 4096. That represents how wide we want our pulse to be. And that's what this pulse width does over here. It calculates it from the value that we were given before. So we take pulse wide and we calculate the pulse width value, which will be an integer, and we use that to control the motor. So we set PWM as the command we use, and we take the motor out. That just comes from the motor that we specified, which one of the outputs on the module. We start at position 0 and we send it the pulse width, the value that we've calculated over here. And then in the loop we simply call the move motor command 4 times, one for each motor. So on motor A we've assigned control A to motor A, motor B, control B to motor B, etc., etc. And we just go through that loop over and over, read the values of the 4 different controls, and assign the position of the 4 different servo motors accordingly. So now let's take a look at this in action, controlling the MeArm with the 4 potentiometers. So now let's control our MeArm. Each one of these pots is controlling one of the 4 motors. And so, as you can see, this one moves the base motor. And this one moves the left motor. This does the right motor. And this does the motor on the gripper over here. And so now I can manipulate my MeArm. Using the slide pots on the breadboard over here. Now here's my PCA 9685 module connected to my Arduino just with 2 wires with the I2C bus. So as you can see, this is a very effective method of controlling multiple servo motors with a single Arduino. Alright, that about wraps it up for today. I hope you've learned something about servo motors and that you've got some ideas for incorporating servos into your own projects. And if you do have some projects you're working on with servo motors, I would love to hear about them. Please leave a comment below the video and let us know what you're working on. Now I've got 3 things to take care of before I go today. The first thing is, if you haven't already, please subscribe to the YouTube channel. Just hit the little subscribe button below this video, and that way you'll get to know every time a new video has been released. You'll also make me very happy, and of course a happy workshop is a great place to be, so please subscribe if you haven't done so already. The second thing you can do, which will make me even happier, is to subscribe to the workshop newsletter. You'll find a link below the video to the DroneBot Workshop newsletter, and this is my way of keeping in contact with you, to let you know what I'm working on in the workshop, and to also find out from you what it is you'd like me to create, what kind of videos and articles you would find the most useful. And so please subscribe to that. All it takes is an email address. And the third thing I would like you to do is to visit the article that's accompanying this video. You'll find a link to that as well below the video, and you'll find all the code from everything that we've done today waiting for you on the article, an easy to download zip file, details about servo motors, and about all kinds of other things on the DroneBotWorkshop.com website. So please visit that as well. Until next time, take care of yourself, and I hope to see you again soon in the workshop. Goodbye for now.